All right, let's talk about the hidden language of our planet. I'm talking about these invisible pulses of energy that travel from the very core of the Earth all the way to the cities we live in. These are seismic waves, and believe me, they have an absolutely incredible story to tell. So let's just start with a huge question. How in the world do we know that the Earth has a liquid core? I mean, think about it. We have never, ever drilled that deep. We've never sent a probe. The heat and pressure down there are completely off the charts. So how could we possibly know what's going on thousands of kilometers down? Well, the answer, believe it or not, lies within the earthquake itself. Yeah, the same forces that can be so destructive are also our single greatest tool for exploring the deep Earth. They act like messengers, carrying these secret clues from the core right up to us on the surface. So what exactly is a seismic wave? Well, at its core, it's just a pulse of energy. When a fault breaks, it sends this energy radiating out in all directions. You can think of it kind of like a sound wave. The wave itself travels, but the rock it moves through just kind of wiggles for a moment and then goes back to where it was. And it's not just one simple wave. Oh no. An earthquake unleashes a whole family of them. And each one has its own personality. It moves differently, it travels at a different speed, and it tells us a totally different part of the Earth's story. So let's meet the family. First up, you've got two main groups, body waves and surface waves. And the names are a total dead giveaway. Body waves, they dive deep, traveling right through the body of the planet. Surface waves, on the other hand, stick to the surface, more like ripples on a pond. Now, the body waves are the sprinters. They always arrive first. But the surface waves, even though they're slower, they're the ones that cause the most shaking and the most damage, right up here where we are. Okay, let's dive a little deeper into those body waves. You have P waves for primary, which are the fastest. They push and pull the rock, kind of like a sound wave. Then you have S waves for secondary. They're slower, and they shake the ground side to side, like if you were shaking a rope. But this last row, this is the absolute key to everything. P waves can power through solids, liquids, and gases. But S waves, they can only travel through solids. Remember that. That one fact is about to solve our planet's biggest mystery. And what about those damage dealers on the surface? Well, you've got love waves, which create this nasty side-to-side snake-like motion that is just brutal for building foundations. And then you have Rayleigh waves. These create that classic rolling motion that you might picture, sort of like being on a boat in the middle of the ocean. Together, they are responsible for the most intense shaking we feel. Okay, so we have this whole crew of waves, all traveling at different speeds. The super fast P wave shows up first. And then sometime later, the S wave rolls in. So what? How does that simple fact actually help us? Well, it gives us an incredibly powerful and amazingly simple tool. For every second of delay between the arrival of the P wave and the arrival of the S wave, the earthquake was about 8 kilometers away from you. It's like a seismic stopwatch that tells us distance. It's genius. And using that, we can pinpoint an earthquake's origin with a method called triangulation. It's basically geological detective work. Here's how it works. A seismograph station feels the P and S waves, calculates the distance, say 100 kilometers, and then draws a 100-kilometer circle on a map. The quake is somewhere on that circle. Then a second station does the same thing, drawing its own circle. Now you've got two spots where they cross, getting warmer. But when a third station draws its circle, there is only one single point on the entire map where all three circles meet, and boom, that is your epicenter. Finding where an earthquake happened is, it's amazing. But it's just the beginning. The truly mind-blowing stuff starts when we look at the paths these waves take through the entire planet. This is how we get back to solving that big mystery we started with. The biggest clue we ever got came from something called a shadow zone, and it's exactly what it sounds like. It's an area on the other side of the planet from an earthquake where, for some reason, the seismographs stay quiet. They just don't detect the waves. It's a seismic blind spot. And here's what scientists figured out. There's a zone where the P waves don't show up because they get bent or refracted as they pass through some major boundary deep inside the Earth. But the real smoking gun is the S wave shadow. It's way, way bigger. Because past a certain point, S waves don't just get bent, they vanish. They stop cold. So let's put it together. The complete and total disappearance of S waves across a huge part of the globe could only mean one thing. They must have hit a massive liquid barrier that they simply could not cross. And that was it. That was the smoking gun. That is how we know with absolute certainty that our Earth has a liquid outer core. So these waves, they paint this incredible picture of the Earth's core, and they help us locate the quake. But their journey isn't over. The final and, honestly, the most critical part of their story is what happens when they finish that journey and arrive at the surface, right under our feet. And to really understand this, we have to look at one of the most tragic and, frankly, most important earthquakes in modern history, the 1985 Mexico City earthquake. Now, this was an absolutely massive, magnitude 8.1 quake. But the really weird part? The epicenter was over 350 kilometers away. So why in the world was the destruction in Mexico City so complete, so catastrophic? The answer is a single powerful principle from physics: resonance. You already know what this is. Think about pushing someone on a swing. If you time your pushes just right, at the swing's natural rhythm, you can send them soaring with almost no effort. Well, the exact same thing can happen between the shaking ground and a building. And in Mexico City, this created a perfect recipe for absolute disaster. You see, the city is built on top of the soft sediments of an ancient lake bed. As those seismic waves traveled through this soft, almost jello-like soil, they got amplified and they slowed down, creating this long, rhythmic shaking. And that rhythm just happened to perfectly match the natural swaying frequency of mid-rise buildings, anything from about 6 to 15 stories tall. So the ground and those specific buildings got in sync, amplifying the shaking more and more until they collapsed, while shorter buildings and taller skyscrapers right next to them were often left totally unharmed. So the lesson here is just profound. The magnitude of an earthquake is only one part of the story. The geology right underneath your city can turn a distant rumble into an absolute catastrophe. It's a critical lesson for engineers and city planners all over the world. From the liquid core to the soil beneath our cities, seismic waves are truly the pulse of our living planet. And we've learned to read that pulse with incredible precision to decipher the story it tells us after it happens. The question that remains, the one that drives scientists today, is: can we ever learn to predict the next beat?